Hey there, it's Max Doolin. This is the second DSA challenge from the 6th year of the Spokane Cyber Cup. In the first challenge, we just digitally signed some data, and that was it. Now you know how DSA works, we're starting to hack it. We start to mess around with it some more. In this challenge, it's your goal to recover the private key. Let's read the prompt. Once the nonce of a signature is known, the private key can be recovered. Recover the private key from the following public key and signature. The flag is the private key. In the previous challenge, this was A, right here, 70. So our goal is to recover this. This is a really important value in DSA. Without this, you can't actually do the thing. You actually can't sign stuff. So that's one of the really big secrets of it. Most of the other information is public, and then the nonce needs to remain secret, I believe, and that's what this has happened here. Somehow, some way, the nonce is known to the attacker, and so your goal is to use the nonce to recover the information. Now we have linked a really nice article for this. So this article talks about a situation where an OpenSSL pseudorandom number generator bug led to the random seed only being 15 bits. And because this is brute forceable, that means that we can try to guess the nonce. And it's to the 15th power. It really isn't that many things. So we can just try over and over again until we're actually able to recover the key. In this case, we know the nonce. We don't need to guess it, but I still think this is a really interesting article, and it shows that small little things in cryptography can really be horribly destructive. So here, it actually has a really nice little formula for us. And I've also included that in the on the hint. I'm unsure if I'm going to keep that hint, but it's there for now for my sanity. So it's taking S, which is the second part of the signature, multiplying it by K, which should not be known, subtracting the message, and then it's multiplying that by the multiplicative inverse of R, which was the first value that we generated in the last challenge, and then modding it by Q. So all those values are known. If K was unknown, this wouldn't be possible to do. So all we have to do is do the math ourselves. So we're going to do this in Python once again. We're going to do S, which is 57, times K, which is 25. We're going to subtract M, which is 501. And then we're going to multiply that by the modular multiplicative inverse of R. We can see that R is 95. So R is 95 minus 1 to determine the multiplicative inverse. And then the modulus we want to use is Q, which is 103, as you can see up there. And then we want to encapsulate that, I believe. Yep. And then we want to modulate that by Q again for 103 again. And that is 39. If we look at the solution, I believe that is correct. So I don't fully understand why this works. I did at one point. I think all you have to do is take the algorithm and move the various values around. And these values, if you know K, then you're able to recover X. So you probably could do some distribution where if you took the entire algorithm from did I put it there? I don't put it there. If you took the entire algorithm and realized what values you could actually recover, I think you can do the distribution and figure out, oh, well, if I know K, then I can get A out of it as well. So although this doesn't seem very interesting, I think this article really makes it worth it, because this is a real thing that happened, and it shows how brittle cryptography is. And you have to very much know the security properties and stick to them. Otherwise, stuff blows up pretty quickly. So we're actually going to be using this same thing in the next challenge, but there's an extra step to it. So I'll see you in the next video.